Thank you, Timo. Thank you, Sip, for having me. Thank you, all online audience, for being there. So today is the day where everyone brought too many slides. I have ridiculous many slides. Let's see. It's branch and price speed dating. Um, I have no idea where we will be going. So column generation, branch and price, in my view, is about two things, or maybe about others. So it's extending your modeling capabilities, MIP modeling capabilities. I will only talk about mixed integer linear programming today, and about algorithmically exploiting, let's say, subproblems you see in your model. So these are the two aspects. Let's see how this shows up. So this is an unavoidable example. It's the cutting stock example. You probably know this as a problem. It is that you're having, let's say, containers or rolls of raw material. They all have a certain length. You have items that you want to cut from these containers or from these rolls. They also have a length, and you have a demand for them. So here is a kind of a solution where you have these rolls and the different items, and you cut them several times as often as you need them. And the objective is to use as few rolls as possible. You know that problem probably. And so here is a classical textbook model. So actually there is no textbook where it first appeared. We have no idea where this model comes from. So, but this is how you could formulate it. You just have an integer variable, how often a certain item is cut from a certain roll, xij. Then you ensure that you cut as much as you need. So for every item, you're summing over how often the items are cut from all the rolls, and you cut as many as you need at least. Then you say, okay, but from each roll, I cannot cut more than there is capacity. So you have these knapsack constraints saying that whatever I cut from a certain roll, it will consume a certain width. And this cannot be more than the length or the dimension of the container. And this cannot be more than I have space. And now, in order to count how many rolls you will use, you will need an extra variable that the capacity of the roll is only available if you use it, and this can be minimized in the objective function. So classical model, right? By the way, never hold back your questions. So if you have comments or remarks, just shoot. Okay, so this is the original model. We can do some observations on this. So it has easy to solve subproblems because it contains many knapsacks. We know how to solve knapsacks, maybe even with dynamic programming. So this is something ideally we wish to exploit algorithmically because it's an easy to solve subproblem. Moreover, all these subproblems are independent because I have subproblems for every role. So I could solve the knapsack problem for every role independently if there was no coordinating constraint that that holds everything together, which is the demand constraint, right? So I cannot arbitrarily pack my roles. I have to cut as many items as there is demand. Comments on this? Questions? Okay. There's another drawback, which is the symmetry in the role. So you've heard about symmetry already. So I can do a permutation of my role indices, and I will get essentially the same solution, which is better lip solving. So you can deal with this, but we try to avoid this. Here's a different idea how to model this. It dates back to at least these three people. Kantorowicz had it already like 100 years ago, really, almost. Okay, 85, but still, Gil Montgomery, you cannot see it, they had it in the 60s. So they looked at it from a different point of view. They looked at what can I do with one role entirely, right? So they were just asking, so if I have only one role, what can I cut from it? So like here, I'm just enumerating all the possibilities. So I can cut the first item once and the second item twice, or the other way around, or only the second item or the third and the third item, or whatever. So I enumerate all the millions of possibilities. Why not? On paper, I can do this, and I can represent this pictorially, or for example, as integer vectors, like encoding all the possible patterns that how I can cut a roll. So 1, 2, 0 means cut the first item once, the second twice, the third not at all. So I can perfectly encode all the possibilities easily with these integer vectors. So they are non-negative numbers, as many as I have items. And together they have to fulfill the knapsack constraint. So these are all the possible patterns, maybe 2 billion, I have no idea, right? But what can I do with this? Well, I can build a model on this idea by introducing a variable that says how often will I use one of these specific patterns. So I have billions of variables now because I have billions of patterns, but on paper I don't care. And with this, I only have to ensure that my demand is met. So for every item, I just say, okay, how often does a certain item appear in a pattern? How often do I use that pattern? I'm summing of all the patterns. That gives me the number how often I have an item, and this must be at least the demand. Minimizing the number of used patterns, because I will have one pattern per role, is exactly minimizing the number of patterns of roles. Right? It's a different idea. It's even smaller on paper. In practice, it's larger because this may not even fit in memory. So because I have so many variables, because I had so many patterns. Okay, so the question is, so this is an integer program with a huge number of variables. How can I even solve only the LP relaxation when it does not fit in memory? And this is where column generation comes into play. Okay, this is a technique you must know. It works for any linear program, so it's LP solving. So here is a linear program with many variables. So this is what we assume. So J, the index set of the variable is huge. And what do we optimizers do? We see trouble, we run away. So think of branch and bound. If you don't know how to solve an integer program, we discard integrality and solve the LP. Maybe we are lucky. If we have so many constraints and we don't know how to deal with that large number, we drop all of them, and maybe we are lucky, maybe they are fulfilled anyway. So we are betting our luck. And so here, when we have so many variables, maybe we don't need most of them because most of them will be zero in an optimal solution anyway. So why not starting with just a small subset of the variables and have a lucky shot? Maybe. This is certainly, I mean, it's just a small difference, but now I have a few variables. It's called the restricted master problem that we are trying to solve, and we can solve it, for example, with the simplex method. Okay, we will get a solution. We will also get a dual solution. So you have seen this several times. And maybe this solution already solves the model with the billions of variables. Maybe. How would we know? Well, we have to check the optimality criterion, and we know how it looks like. It's the reduced cost of all the variables. So we have a formula for this, which is, so this is what you have to remember always. It's the original cost minus the dual variable vector times the coefficient column. This is the reduced cost of a variable, and when we are minimizing, all these should be non-negative. Oh, this suggests a proof. Oh no, not. This suggests an algorithm, let's say. So we solve the restricted version of this with just a few variables. We get a solution. In particular, we get a dual solution. We use the dual solution to compute the reduced cost of all the variables we have ignored so far. And if there is one with a negative reduced cost sign, so then we add the corresponding variable. We have one more in our restricted version, and then we iterate until at some point when we compute the signs of the variables we have ignored so far, there is none with negative reduced cost, and then we stop. Then we have a proof that the solution is optimal for the full problem, and hopefully we have not generated all the variables. Comments? Questions? Problem is this: compute the sign of all the variables, because I mean these are billions of variables. We cannot compute the sign of all the variables. This is the second rule that we optimizers never do. We never explicitly enumerate. Right? So whenever there is an explicit or a complete enumeration necessary, we switch to an implicit enumeration by formulating an optimization problem. So I say I'm interested in the smallest reduced cost value of all the variables, and just casting it as an optimization problem. This is called the pricing problem or sub-problem or column generator or whatever. And when this minimum is negative, then I have identified a variable which is attractive, I would add to my restricted master problem. And when this is non-negative, I know when the smallest is non-negative, there is no negative, then I have my proof of optimality. Okay, so this modifies this just by a little bit. Instead of computing the sign of all the variables, I compute the sign of the most negative one. Correct? And this is sufficient to keep the iteration going. So this is column generation, and we could summarize this as differently, but I hope you got the idea. Comments? Questions? So this is easily implemented against any API of the solvers. So you can use your favorite solver. Your favorite solver is Skip, but you can use also your non-favorite solvers, and they all work. Okay, so this is an idea which has been around like the late 50s in the Western world, and Eduardo, he will arrive tomorrow evening, and he will tell, he found out with Ruslan Sadikov that this has been around in the Soviet Union and even in use in the Soviet Union even earlier. So they did column generation way before we did it in the Western world. Here's how this could look like. So because I just said, okay, let's minimize over all the columns. So let's look how this looks specifically for this formulation. So what I'm starting from is it's an LP relaxation, right? With only a few patterns. So I have only a few variables in my restricted master problem. So some of the patterns are already there. And I can solve this linear program, and I will get a solution and a dual solution. And with this, I can, well, at least write down the reduced cost formula, which is the original cost. So every variable is cost 1 minus dual variable vector times coefficient column. All these should be for all the patterns, should be non-negative. Okay, so I cannot explicitly enumerate, but the question? Column generation is about solving LPs. I have it explicitly on some slide. When people say, I solved my integer program by column generation, they always lie. Except it's a special case. No one solves integer programs by column generation. It's an LP solving technique because it's based on an LP optimality criterion. Yes. I cannot use half a pattern, but what do we do with a LP relaxation? So then we didn't have to branch. This is what comes in the, well, around 2 o'clock, I would say. Yes, but you're totally right. We're solving it, and thanks for this, because I cannot stress it enough. It's an LP solving technique. And as I said, so this is what I want to compute for all the patterns, and I cast it as an optimization problem by saying, well, this is the objective function. It's a linear objective function. I want to minimize the reduced cost over all the patterns. And thankfully, I know exactly how the patterns look like, right? So we said these were integer vectors, non-negative, and they have to satisfy a knapsack constraint. So we know how these numbers look like. And so I can cast this as an optimization problem and slightly modifying it makes it even more obvious that this is a knapsack problem. Remember, so that was one of the things we had observed. Well, the cutting stock contains as a sub-problem the knapsack problem. We know how to solve that. It would be so nice if we could exploit that knowledge. Here we can exploit it. Because now you can even solve that by dynamic programming. It's formulated as a MIP, but you can use your favorites, a specialized solver for that. Cool. Okay. Questions? 2 cases. So as we said, could be negative, then we have a pattern that we add. Otherwise, we have the proof of optimality. Okay, another example. And this is closer to what you will be doing in the afternoon. You will be working on the bin packing problem. The bin packing problem is a specialization of cutting stock where you have demands of 1, but this in a sense is closer. It's a graph problem, undirected graph. You want to color all the vertices, so assign colors. There are 2 rules. Every vertex must receive a color, and neighbors must receive different colors. So this is the vertex coloring. It's a hard problem. Like everything that is fun, it's hard. So we can easily write down like the textbook assignment model for this, again, just as we did. So we have the available colors. Let's say we have a set of colors that we can use, and then we have assignment. Will I use a certain color for a certain vertex, yes or no? So that's the typical assignment thing if you start modeling, right? Will I use the color? And then you can say, okay, every vertex must receive a color. So from the selection, I must select exactly one. Neighbors must receive different colors, so I cannot use the same color for the endpoints of one edge. And then again, in order to count the number of colors, we have to do this construction. Will I use a color? I have an extra variable for this, and I cannot use the color, so I cannot assign the color. So this is this linking here. I cannot assign the color. If I don't use the color, or other way around, if I assign it, I have to use it, and then I can minimize that number in the objective function. So the same mechanism. This will compute an optimal coloring. It will not do so very well because this is a horrible model. First of all, the LP relaxation is super weak. So again, the LP relaxation is what we need in branch and bound. It's the number one thing that you do. And you look at the LP relaxation, it's totally useless. And what is more, also this model is totally symmetric because when you're permuting the colors of a solution, you will get a different solution, or the same solution actually for us, but not for the solver. And this is both is very bad. So these are not only, let's say, theoretically hard, these problems are also computationally quite challenging. But we can look at it again from a different perspective. So more globally, looking at the solution and look at, for example, the yellow vertices. What do they do in the graph in a solution? Well, they form an independent set. And they should, right? It's a coloring. So they should, if you have two vertices in the same color, they don't share an edge. So you can recast the vertex coloring problem as partitioning the node set into independent sets, into stable sets, as few as possible. That's the same problem. And based on this, well, we can try to derive a pattern-based formulation, just as we did for cutting stock. We look at all the stable sets in the graph and how we can encode them. Well, again, as vectors, I have entries as many as I have nodes. This time I only need binary. Will the node appear in the stable set, yes or no? And so then I have binary vectors, and the only thing I have to enforce is that when there are two entries belonging to the endpoints of one edge, I cannot have them both at one. Right? So this is the stable set part of it. And based on this, we can do it just like we did. We will have a variable for every stable set in the graph. I will use that stable set, yes or no, so it's a binary variable this time. I have to ensure that every vertex will be covered by one of the stable sets, exactly one. So I'm summing over all the stable sets that contain a certain vertex, and exactly one out of these must be taken. And I'm minimizing the number of stable sets. So I'm minimizing the number of colors. This is, well, a very small, nice model. It has many variables because there are many stable sets in the graph, but this is a very nice model. So again, if I would like to solve the LP relaxation of this, it has too many variables, but you can solve it by column generation. I will have the dual variables for every constraint, so there's a dual variable for every vertex. And we do what we just did. We, well, write down the formula for the reduced cost, original cost. It's again one here, minus dual variable vector times the coefficient column, and the coefficient column encodes a stable set. This is what we know. So these are not unknowns to us, but we can precisely describe them. These are binary numbers, and they must satisfy the stable set constraint. Right? So again, this is how the optimization problem looks like. It's a maximum weight independence. It's not easy to solve just for one variable, but at least I can do this. So if I have a stable set solver, it would be nice to use it here. Comments, questions? Okay, so this is what column generation does. I will skip maybe the example here. And we could talk about many, many things about the algorithms. So probably this afternoon you have to initialize this. So where do the first columns come from? So you could, for example, just say in the vertex coloring problem, I start with some stable sets. And for example, you could start with all the singletons. Every single vertex is a stable set. That would give you a super expensive solution. But anyway, this is something to technically start from. Why not? You may have a heuristic, you may have other things. So let's not go into details. A practically important problem is that it may happen that you have several types of variables, let's say. So for example, you have different vehicles, or you have, let's say, different roles of different capacities. So you will generate patterns that somehow fit into the smaller roles, and patterns that will only fit into the larger roles. So pictorially, it looks like you have different, let's say, kinds of variables. So maybe belonging to different capacities of your containers, let's say. And that means you also have different pricing problems, generating variables for all of these specific roles, right? And their optimality is when all these pricing problems report, I do not find any variable, just to have that in mind. Okay. Question is, do we have to invent these models? So I cannot help it. I see these pattern-based models everywhere. So you talk about a problem to me, and I will immediately see some substructures that I could combine and build variables on whatever configurations. But the good news is, so we don't have to invent this on our own. But there is a very automatic technique coming up with such models, and this is the Dantzig-Wolfe reformulation. So I will rush through this, and in the end, I will tell you don't have to know this, and after that, I will tell you you should know this. But anyway, let's look at this. So these three guys, Minkowski, Farkas, and Weil, so they had observed and proven actually that there are two different representations of a polyhedron. The standard form, the one that we know, the outer representation by finitely many linear inequalities, or half spaces, closed half spaces, let's say, or equivalently as the convex combination of all the finitely many extreme points plus Minkowski sum plus the non-negative combinations of all the extreme rays. So instead of having the linear inequalities describing all the feasible points, I get the same set of feasible points by looking at the extreme points, finitely many, take the convex combinations, look at the extreme directions, these are finitely many, take the non-negative combinations, and then I Minkowski sum all of them, and I will get the same set of points. And this is a characterization if and only if. So we say that the convex polyhedra are exactly those which are finitely generated. This is nice. This is just beautiful. So we found it in the literature. Let's use it. And this is what also Dantzig and Wolfe thought when they say, oh, look, there's a theorem. Let's apply it to LPs. And so what did they do? They said, okay, we want to solve a linear program. A linear program typically has several kinds of constraints. So like for assignment, for capacities, for implications, for configurations, for sequences, whatever. So here we say we have two kinds of constraints, ax greater than b, dx greater than d. And one of those we will just identify and say, oh, this is something I want to apply this Minkowski-Weil thing on, because I think this is a subset of constraints, let's say dx greater than d. I think I can deal well with this for whatever reason. And the others are, I don't know how to deal well with them. I call them the complicated constraints. Okay, so I apply this reformulation thing to the polyhedron that is described by a subset of the constraints. Okay, so this is what we do. We have a subset of, so here are all the constraints. So above here, these are the complicating ones, and these are the easy ones, let's say. And I'm reformulating the easy ones as the convex combination of the extreme points, finitely many, plus a non-negative combination of the extreme rates, finitely many. Just on paper, we can do this, okay? Because we can, just accept it, it's mathematical beauty. Why not? Why not? And you can even do this algebraically on paper, so we don't have to go through all these steps. But anyway, so this is what I do. I know by the theorem that I can express every x that fulfills dx greater than or equal d, so it's in the polyhedron, as a convex combination of points plus a non-negative combination of rays. And this is exactly what I just plug into the remaining constraints. Nothing else will happen on the next slides. So this is just plugged in. You don't have to read this. The purpose here is only, it's doable, okay? So we just rearrange a little bit and give these names, and then we arrive at a model that essentially now has variables for all the extreme points of the polyhedron that I reformulated, and variables for all the extreme rays of the polyhedron that I've reformulated. Again, you don't have to understand this now. It's just important. This is doable, okay? Good. Now what I have here is a linear program, as you see, with many variables. I said finitely many, but there are so many extreme points and extreme rays, so we could never again store this in memory. So what did we do? We discovered the theorem. Dantzig-Wolfe applied it to a subset of the constraints because they could, and they did. And now we have an equivalent LP. So it was just a reformulation. It's the same LP still, but we have many more variables. So if we are just after this, we are in a lot of trouble. So why did we do it? Well, maybe because they had seen that we shouldn't be scared because we know column generation. So this is what they knew was around at the time. And that makes it totally obvious what comes next now. So we start with just a subset of the extreme points and a subset of the extreme rays. Right? So this gives me a sort of restricted version of the LP, and certainly I can solve this. I will get a solution, and I will also get a dual solution, which is more important because that defines my optimality criterion. So I can write down the formulas for the reduced cost, and without reading it, you should recognize that it's always like there is a cost of a variable minus the dual variable vector times the coefficient column. It's always the same thing. And you just do the algebra and see you have a linear objective function, which is the reduced cost over something that describes your columns, and you represent extreme points and extreme rays. So this is what we know. We have this minimization over the extreme points and the extreme rays. And how do we know how the extreme points and extreme rays of a polyhedron look like? Heck, well, we do know, or we do get them for free in some sense. Dantzig, after all, invented the simplex method. So when we minimize over what we reformulated, we will, when there's a finite solution, we will be in an extreme point when we use the simplex method. And otherwise, when it's not a finite solution, we will have a direction of unboundedness. So we will have identified an extreme ray. And since we minimize the reduced cost over this polyhedron, we will identify an extreme point of smallest reduced cost or an extreme ray of, well, let's say, put it in quotes, smallest reduced cost. It's not exactly true, but it doesn't matter so much because if we solve this, there are three outcomes possible. It could be that this is unbounded from below, then we have a ray. And we would add a variable corresponding to a ray. Again, don't look into the details, it's doable. Or we will have a finite optimal solution and then of negative reduced cost. And then we have identified an extreme point. It's doable to add the corresponding variable. Or the reduced cost, the smallest reduced cost among all the extreme points and rays is non-negative, and this is a proof that this solves the LP with all the variables optimally. Okay? Again, for today it's enough, it's doable. Comments? Questions? Okay. it's always possible also by the construction. So we say we represent every solution as a convex combination plus a non-negative combination. So when I have a solution to this master problem, I can always go back into the space of the original variables. This is important later when we are branching. Okay, so what did we do? So we reformulated a subset of the constraints. The constraints are those that we reformulated, right, that appear in the pricing problem. So it's an automatism. You just say this will be reformulated. These will be the constraints in my pricing problem. These are also the variables in the pricing problem. And these exactly define how what the meaning of the variables is that I have in my master problem. So this is the way that we were going from this assignment models, for example, for vertex coloring to these pattern-based ones in stable sets. Because what I reformulated there was the stable set constraints, or in the Cantor in the cutting stock model, what we were reformulated were the knapsack constraints. I applied Dantzig-Wolfe reformulation, which is not exactly true, but almost. Because, so block diagonal structures, we already said, in practice, you often have that you have many independent subproblems that are only linked by some, let's say, a common budget. So we have all the knapsacks, they are totally independent for all the roles, but they are linked together by the demand constraints. Or we have all the independent set constraints. So we want to find a stable set in red, we want to find a stable set in blue, we want to find a stable set in green, but they all together have to cover every vertex exactly once. Right? So we often have this structure, and you have it this afternoon also, even though you will not notice, but it's true for bin packing also. And what happens here is that you identify the linking constraints, so this common budget, as the complicating constraints, and the others are typically those that you can reformulate. They are easy to solve. Why are they easy to solve? Well, because they decompose into independent subproblems. It's typically easier. So was, and Timo told you yesterday about this. Okay. We could go through this, but it's absolutely the same. Maybe one special case, you will get, as before, a pricing problem for every color. So let's look into the special case of vertex coloring, what happens here. Because there we have now a subproblem, find stable sets in every color. Right, so this is what a direct application of the Dantzig-Wolfe reformulation would give you. So you have the red stable sets, and you have the blue stable sets, and you have the pink stable sets, and whatever. You have all the stable sets, and you would combine all of them. So this is where you would end up to, and taking from all of these, exactly every vertex must be covered once. So, but now we see, well, how does it matter, or what does it matter, what color the stable set is? So whether it's blue or red, so we don't care. But now we have pricing problems which produce red or blue or pink or whatever stable sets. So we realize, in fact, what the pricing problems do, they give us the same solutions, just different variants of this. It would be wasteful to solve all the pricing problems. So we try to solve only one representative of it, like a colorless pricing problem, right? So what we could do is we just aggregate everything that we have here. So just say, okay, I will use a certain stable set in red, and maybe the same stable set in blue, and maybe in another color. But how often I use it in total, I will represent this by another colorless variable. So I'm aggregating the information, having less variable, and the symmetry in the colors is gone. So this is how we arrived at the pattern-based formulation for vertex coloring. I did a Dantzig-Wolfe formulation on the textbook model, and then I performed this aggregation thing. Okay, so this is the truth. And this happens always, often, let's say, often in practice. And it happened already this afternoon for your bin packing problem. because all the bins are identical, you would have knapsack problems for all the bins. All the same capacity, all the same items. So you would say have pricing problems for all the bins, and they are all the same. So you just solve one representative instead, just one problem giving you packings, and then afterwards you just assign the bins once you have a solution. Comments, questions? I don't believe you, but anyway, so we have to skip. So even if you never ever do the Dantzig-Wolfe reformulation, so this is why I rushed through this. So you don't have to understand it, but you should know it's there in the background, whether you like it or not. Timo has, sorry to disturb you, but Timo has in the T-shirt. The nice thing about science is it's true regardless whether you believe in it or not. So the nice thing about Dantzig-Wolfe is it's there in the background whether you use it or not, right? So you can't help it. It's there. I will just, I know that I'm running over time, but it's, I will tell you in a second. So here is for those who are more on the pictorial side, what we just did. We have the solving LPs, right? LP relaxation, so different kinds of constraints. We reformulated one of them just by iteratively, let's say, extending our model by giving more and more, let's say, extreme points, like in this example. And then at some point, we prove that we have enough extreme points to describe an LP optimal solution, and this gives you nothing else but the same as the LP relaxation. Well, yes, it's a reformulation, it's equivalent. So all this trouble only for arriving at something that we could have had with the LP relaxation. So why are we solving LP relaxations? For the bound. Only for the bound, right? We want dual bounds because we want to prune the tree. So because we want to go to lunch, we want to see solutions. So the better the bound, the earlier the lunch. But this is not what we did. So what we did is we had pricing problems where everything was in integers. Remember, stable set, knapsack, whatever. So everything in practice, the pricing problem is integers. So what we actually do is we solve something else. We solve this implicitly over the convex hull of the integer points that are feasible for the polyhedron that we reformulated. This, we get the extreme points of this, and this is super nice because this gives potentially a stronger relaxation, and this is why we are doing it. Right, so the hope is that this gives a stronger relaxation, and this gives at least a way of arriving at solutions where we do branch and bound. Okay, and this is what we have to do now, because so far, again, we solved an LP. So we solved the root node of the branch and bound tree. So what we have to do now is to do all this stuff, column generation, in every node of the tree. And this is where it's getting troublesome with the APIs of the solvers. This is what you can do in skip, and this is what you cannot really do in all the, let's say, closed shop solvers, because they don't give us one important access, which is something that has to do with the branching. So first of all, we typically have a very, very strong relaxation now. We can make it even stronger with cuts. I will not tell this to you today in the interest of arriving at integer solutions. But anyway, it's doable, right? So this is not either or. It's not branch and cut or branch and price. It is branch, cut, and price, or branch, price, and cut. I never remember the correct ordering. But you can combine this with all the cutting plane business which is around, and it is even enhanced by Dantzig-Wolfe. Whatever, look into this. What we want to do is we want to solve an integer program. Last 5 minutes. Okay, we have to do branching now, right? So you're totally right. We solved an LP. We may have a fractional coloring, a fractional packing, whatever. It's useless, but we have a good bound. Okay, and again, no one ever solved an integer program by column generation unless it was an and it was automatically integer anyway. So we just solved the linear programming relaxation so far. We need to branch. How? Well, number one that people tell you is never branch on the variables that you generate. Never. This would be the first idea we have, because this is what we do in branch and bound, but this is not what we do here, because this gives a very unbalanced tree. Think of the binary case. So when I forbid a variable, almost nothing happens. I forbid a certain pattern out of billions, who cares? Otherwise, I enforce a certain pattern that fixes a lot of the solution already. So one will not have an impact on the bound, the other might have considerably. So this is not good for the balancedness. Worse, and now comes why this is not easy to implement against other solvers where you don't have access to the internals, is the pricing must know about the branching. So if I just decide to down branch on a certain pattern, the pricing must know that it should not regenerate that pattern. So typically we have no idea how to enforce this, and this is why we don't branch on the master variables, on a single master variable. What could we do instead? And here is where the Dantzig-Wolfe comes. So it was there all the time, because so our master problem arrived at a Dantzig-Wolfe reformulation, and we know how to restore the original variables from the master solution. So I have a fractional solution here, and I can translate it back to the original variables I was interested in. And maybe I'm lucky, and these are integer already. It could happen, and I'm done. Often enough, I'm not, but then there will be a fractional x, and I can branch on that. Good, like standard branching, branch down, branch up. And here we have two options how we could do this. Number one is we could explicitly, well, think of this as a constraint in the original Dantzig-Wolfe formulated. Then we have an additional constraint in the master that would give an additional dual variable we would have to respect in the pricing. So this is one way of doing this, but it's easy to respect in the pricing actually. It only affects the reduced cost, only the objective function. The remainder usually, let's say usually, stays the same. So this is easy to be done. Or even easier, you put the bound directly in the pricing problem. So you will never generate anything that is forbidden by the branching. Then you have to additionally remove all the columns that contradict your branching decisions. But this is easily doable. Okay, this is original variable branching, and it always works. But now you say, yeah, but they never did this Dantzig-Wolfe thing because it was so complicated and so. Well, you did. You always have these original variables. So some people say, leave me alone with Dantzig-Wolfe. I just have a master, I have a pricing problem, I do just column generation, I don't care about. But you have the original variables. These are the variables of your pricing problem. Remember, they are there. So you can branch on these values. You just have to do the transportation back into these values. And then do you remember the formula? And then you have the values of the original variables, and you can branch on that. There's one trouble, which you will have in the afternoon when the mass is aggregated, because this is not what we see. So our master problem did not solve this problem here. So we arrived at stable sets, yes, but not in colors. So what we had is this situation. So this is a partition into stable sets, but you can, I mean, we could see which, but we don't have colors. So if we want to transport this back into the assignment variable with a certain color assigned to a certain node, then this is not doable from here, unless we try to do some tricks. So what we could do is we could take the stable sets. They all have a certain value in my LP relaxation. And I could try to, let's say, create variables for all the stable sets again in the different colors. What values would I give? Maybe I take the value of a stable set and just evenly distribute it among all the colorful stable sets. It's horrible, but it would work. from this, then you could just say, okay, now I have stable sets in certain color, and then for every vertex, you just sum over all the stable sets that contain a vertex, and this gives you the original X vertex color variable values. The original values you could branch on when they are fractional. What could happen is that now, because our pricing problem does not know about colors, now you branch on a certain variable, on a certain node that must be in a certain color or not. Now the pricing problem must generate stable sets in that color. So maybe you have to introduce, again, colorful pricing problems, reintroduced, enforced by your branching, in addition to the colorless branching pricing problems. So, but it's doable. And the good news is this always works. It's a complete branching scheme. So if necessary, you could disaggregate first and then branch on the original variables, and this will always give you an integer solution. But so we could do the disaggregation in a much better way, yes, but the drawback is the colors come back. So the symmetry comes back. And then, so this is the second to last slide. What is suggested alternatively, branch on the master variables. Didn't I just say we shouldn't do this? Yes, on single ones, not. But we can always assume, so I don't tell you why, but we can always assume that the master variables in the final solution will take integer values. So that in particular means whatever subset of the variables I take and sum over their values, this will be an integer value, finally. So the idea is identify a rule or provide a rule that identifies a subset when I have a fractional solution in the master, that identifies a subset of the variables, which gives me or is guaranteed to be fractional. And when I have such a subset, so this is this J hat here, then I can branch on the sum of the variables that are contained in this subset, right? They have a certain value currently, it's fractional, so I branch down or branch up. This can be respected in the pricing problem. So all this is doable, and François van der Beek has wonderful papers on this. You should read that. It's generic, it happens, it works always. You probably will not read into this, a shame on all of us, because there are special cases that appear in practice, like set partitioning problems like this afternoon. So we don't have to learn about the beauty of Van der Beek rules and look into special cases instead. So what Ryan and Foster said, and I believe this is useful for your afternoon as well, is they identify, so when we have a fractional solution now to a set partitioning master problem, like for vertex coloring or for bin packing or for vehicle routing or whatever, so it appears very often. If we have a fractional solution to the LP relaxation, then we know that the subset we can identify is there are two constraints, two rows, where when I'm scanning the entries in these two rows and I count only the variable values where both entries are at 1, this will be a fractional sum. So this is what Ryan and Foster had proven. So two items are together in a set, two nodes are together, two items are in your knapsack together. I'm summing over all the variables that have both. This is a fractional sum, and you can down or up branch on this. And what Ryan and Foster had seen is that this can be easily incorporated into the pricing problem directly. So you do not have to put any master constraints at all. The branching is accomplished directly in the pricing by saying, well, I take both of the items that I have identified where the fractional sum arises, or I take at most one of them, or same and differ branches. And this works so often that we don't have to look into Van der Beek. What a shame. But well, that's, maybe when you encounter something more complicated, you will look into these other rules as well. So if you have more minutes, Lagrangian relaxation and how it relates to all this is certainly helpful. Bender's decomposition in energy is so important to look into this. And the good news is, so Eduardo will arrive, Eduardo Hua. They have a super nice resource on this. column generation. It's on GitHub. You can download it for free. It's a wonderful book full of expertise. And it's free. And the second one is our book. So it's a coincidence. We both wrote years on this. You know, we go out on the market, so to say, and in the same year. We have also one in Branchenfeld, it's also free. So you can download it at the Girard if you want to learn more. True. Okay. Thank you.